So thanks a lot for inviting me and giving me the chance to present the task 32. I'm always stopping a little bit because formerly it was called Annex 32 and they switched the name because now we have all tasks. And so if I would say Annex 32, it's the same as a task 32, but sometimes I fall back to the old definition of Annex and not to the task. So we have the task 32. It's modeling of energy storages for simulation, optimization of energy systems. And we gave it the nice name Open Sesame, from open source energy storage models. So the acronym is I would say, more or less fitting to the longer title. It's started now more or less with the begin of the Corona pandemic. So it was, I would say, a very big challenge to organize this, because we planned this annex or this task without any Corona pandemic. And so we started it in this pandemic phase. And so it was very difficult to get on track and to come on. And so it takes its time to get first results. So I would say my aim today is to give you an overview about the aims of this Annex 32, to give you information what is the status quo at the moment and where we want to go in the nearest future, because you can see it's finalized probably in April next year. As you know from the IEA tasks, this is more or less an aim. We try to meet this aim, but in most cases there's a little bit gap between the, I would say, official aim and the realistic aim sometimes. So my internal aim is to get the finalization in summer next year, but let's start with April. So let's come to some main points. I try to give you an overview in a nutshell on the first slide to show you what is the main aim and then to go a little bit more to the details. So let's start with the situation. So energy systems are changing. You know, we started this without changing of all the questions of natural gas and LNG and so on. We started it from the normal change because of reduction of CO2 emissions, the change to the renewable energies and so on. As mentioned, decarbonization, decentralization, cross-sectoral approach. That means more focusing on the electric systems from wind and solar and using, for example, heat pumps to make it cross over from electric to the heat system. So the main challenge is, if you want to model some energy systems, you need models for energy storage devices. And we saw a lack of very good scientifically proven open source models always on the same level. So it was not easy to find them. And so we defined the task for us to develop this type of standardized storage models for various applications. The result we are aiming at the moment is to have generic open source models and also data sets to bring these data sets to the models. I will explain it afterwards a little bit more in detail. Let's switch to the right side. What is the scope? The scope are electrical storages and thermal storages. This end is very important because in most cases there's a more or less bigger gap between both communities, the electric community and the thermal community. Many researchers are working on thermal storage and others are working on electrical storages. But there are really only a handful of researchers working on both. That's the problem there. And so we try to bring both sides together here. And the focus for electrical power storages was pumped hydro, compressed air storage, then lithium-ion batteries and vanadium redox flow batteries. The lead acid batteries mentioned here, we skipped afterwards because it's not part of the, I would say, future energy systems. It's the technology of the past and probably of some applications in presence, but not of the future. For thermal storages, it's a little bit more difficult. It's also the hot water tank, stratified or mixed. We have PCM, that means phase change materials, and also seasonal storages like boreholes, pits, and so on. So probably I can skip this point a little bit to save time to you, because this is more detailed what I have said on your first slide there. And I want to bring you to the main point. the different model levels. I think this is the main point. We have had a long discussion on this because we are coming from the application. The application means if you want to apply an energy storage model to a bigger environment, for example, you have a huge model for Western Europe and you want to apply a storage device to this model, you are not allowed to make this model too complicated because otherwise you can't run the optimizer for this big system of all the different devices existing for generation, consumption of energy in Spain, Germany, France, Greece, and so on. It's not running. So you need some simplified systems, but it must be accurate. And so we defined it from the left-hand side, starting with a level 3. This is our definition, to be honest. We called it, this is the very high sophisticated physical or chemical simulation model. So this is existing models. These are existing models for example, lithium-ion batteries, for compressed air storages, and so on. This is in most cases existing, but this is much too complicated. We have an own model, for example, for compressed air. We are able to optimize the different shape of the blades of the compressor. And no one who is running a big optimization system is interested in optimizing the shape or the angle of the different blades of a compressor stage. So our aim was to derive from this level 3 a level 2 model. It should be mixed integer and it could be nonlinear. It's possible. And with this model, this called level 2 model, we want to go to, in most cases, to simulations, mostly in a smaller scale. That means for a region or for a city or for an industrial site or something like this. It's a small application and for simulation, because in simulation, you can also act with mixed integer nonlinear. For everybody who's not a mathematician, mixed integer means there are some figures like 3.1, 3.5, but also 0 and 1. That means it's existing or non-existing, like something like this. So this is mixed integer, and nonlinear, I think it's clear. So it's like x square or something like this. And from this level 2, we want to have another level. We call it level 1. This should be mixed integer, but linear. The reason is if you want to go to this mentioned before, big systems modeling, then you have to have a mixed integer, but always linear approach, because with a nonlinear approach, all the big models are not running. It's too complex for them. This is here highlighted in this, I would say, red zone. This is our aim of our modeling in this task. So on the left-hand side, level 3 is existing. We are looking at level 2 and 1. And to make a clear separation, what is also existing, we call it the level 0 or level -1. You can accept, this was defined afterwards. Level 0 means in this case, you have only a constant. There's nothing linear or something like this. This is sometimes existing. That means you have a storage device and this has an efficiency of 0.81, for example. So 81% efficiency, that's all. That's the whole definition of the system. This is existing, but you can imagine this is a very simplified system. So you can't simulate or operate the system, because if you have, for example, a battery system, if you're running this with a high power charging or discharging, the efficiency will go down. Also lifetime will go down and cycle time will go down, but also the efficiency. If you're running it very smoothly, you will have a higher efficiency, longer lifetime, and so on. And to integrate this, you need the better level 1 or level 2. And the most simplified, it was a level -1. We call it, this is only an annual sum. So you can only probably calculate and say, okay, we will store 3% of your energy and you have to store it. That's all. So but this is not really simulation or not optimization. It's not, both not. So coming back, we are thinking this is level 1 and 2, and we want to derive it from a highly complicated and a high sophisticated, realistic, complex model. So I hope I haven't lost you, because it's also very important for us to make this definition and to aim on these different levels there. And the next and last slide to this problem was is shown in this zoom in for the demonstration application. Our general description you can see for the level 1 and 2 is always to give something we call it, or it's called mathematical pseudocode. So it's in description on the mathematical level and it's written in a pseudocode. So it sounds like a language we can introduce it by Python, for example. So this is then the next level to say, okay, after we have the mathematical description of these storage devices, we will go to demonstrate the functionality of this description, and we try to make the programming in Python and probably showing it that it's running in a bigger environment. For example, it's called ÖMOF. This is a system you can simulate energy systems on a smaller scale, or on a simulation scale, that's correct. Or we can run it by pipe SA. This is a system here for optimization. This could also apply it to different systems like GAMS in the remix model from the DLR, who is a participant in our group there. So let's come to the next point. We called it the open source. That's very important. We want to give all the results and all the modeling as an open source to the open source community. And so we are looking at this Creative Commons legalized system here, or the legalized system here on the right-hand side. And we decided to go to a platform after this project to give it really to everybody, everybody could use it, everybody could modify it, and so on, and remix it, and everything will be allowed. This is the aim. It's not our own system at the end, it's a system for everybody. So we defined some major outcomes there, and as mentioned on the first slide, we want also to give some simple test cases based on data sets to make it more clear. If you had a model, you want to run it, and if you want to run it, you need something going in and going out. You need an energy production generation on the one hand side, and you need an energy demand. So for different applications, we are looking for demand or generation profiles of the one hand side, and also on the other hand side, what is coming from a windmill, from solar PV, or from a conventional power plant, to give you the chance to use this different models in this environment with data sets. And we want to demonstrate all the models in an open source language. That was also very important to say. We want to show you that all the models are really working at the end. And last but not least, we try to make some practical applications there, in this case, in existing system models, and to answer some really burning questions there. And we have here some, I would say, exchange or cooperation with the IEA headquarters there. It was now the follow-up from Luis Munera. This is the former guy. We have the cooperation with Times Markal Group here from the ETSAP group. And so we try to get the best out of this cooperation. And this is also the highlighted part here. The results will support a common understanding of energy storages and the economic and system value. I think this is a very, very important point, because no one has a problem to explain why photovoltaics or windmills are very important, because we need renewable energy and we have to produce it, so you need some generation units. That's it. By the storage device, it's not needed by itself in most cases. It's only needed by itself probably for your mobile phone or for your notebook or something like this. But if it is grid connected, it is not really needed by itself. It's only needed because of some imbalance in the grid or in the heating devices and so on. So it's not really a need from its own. And you have always to explain why it's a good choice to integrate an energy storage on the electric or on the thermal side. Let's jump over this and go to the 2 slides of the structure of this task 32. So this is our time plan. We have 3 years. In the first years, we started with subtask 1. The aim of subtask 1 was and is to get the input data. So we are looking for standardized data sets for demand and power generation profiles for different regions, and we want to make it open source. And this will be also a result at the end on the right-hand side here. Then we started in year 1 also the storage model and data. This is the mathematical description on this mentioned 2 levels in a mathematical pseudocode. This is, to be honest, not only running in year 1 and 2, it's also running now in year 3. We are not as fast as we wished. And this will be also a final result. And what is going on since, I would say, year 2, but now in year 3, I would say mainly the application. That means trying to use the different models and to get information out of this modeling. And this application also includes at the end the publication of the results. And this is not only done by me. I'm only the task manager. I'm the gray guy here, gray in both cases, my hair and the box. But we have 3 different subtasks. And for subtask 1, we have 2 subtask leaders. It's Yvonne Scholz from the DLR in Germany, and it's Darren Zhang from the NRC in Canada. And there's going in various data sets for generation and demand for different regions. They are existing, and we're getting out this open source, double-checked, simple test cases based on this data sets in a standardized format. This is very important because there are so many data existing, but we have to have it in a standardized format. Then we have the subtask 2, storage model and data. So we have also 2 subtask leaders. We have Claudio Brivio from Switzerland, from CSEM, and we have Ian Beausoleil-Morasson from the Carleton University in Canada. This is for left-hand side is for electrical devices. Ian is for thermal devices there. Input for this subtask is then the existing very detailed models, so the so-called level 3 models for thermal and electrical devices, and outcome is this open source coherent mathematical models written in a pseudocode. Coherent means in this case, if we will have a simulation with level 2, more or less with typical parameters, we want to get the same result as from level 3 models with typical parameters. Keep in mind the difference is with level 3, we will be able to make great variations on very untypical parameters. But this is not the aim of our level 2. We want to derive, this is more or less the middle of the road, always typical parameters and not very untypical. And coherent means also that we go to level 1, that this simplified level 1 model is also fitting to the results of level 2, but it's not able to make it as complex as level 2. So we have always to have it coherent if we have some parameters in the middle of the road. And the last subtask is subtask 3, the application. There we have 3 subtask leaders. You can see we have Champu. It's also from the NRC in Canada. We have Natisha McRae from the NRC in Canada, and we have Alireza Afshari from the Aalborg University in Denmark. And there's the difference between large-scale systems and small-scale systems. And this includes also the electric and the thermal side here. So as I hope you have a picture in your mind how we try to collaborate in this annex in the different subtasks. And you have seen the subtask leaders by picture. So in the next 9 slides, I try to go to the details of our task 33 from Open Sesame. Let's start with subtask 1. So there we try to develop this different database. You can see it could be tables like this, or it could be graphs like this. We want to have the test cases or time series on a resolution of a quarter-hour to 1 hourly level. It depends a little bit. For the electric side, it makes sense to go to the quarterly hour level. For the thermal side, probably the hourly level is fine enough for us. And we want to get this typical generation curves for renewable energies in various countries. That means we want to get the data, for example, to say we have a windmill in northern Denmark, or we will have photovoltaics in the south of Italy. And then we want to get from this data set the correct data set for the generation by wind, PV, and so on. And on the other hand side, we started to say we want to have test cases for typical demand curves for typical users. Nowadays, we have learned this is very difficult. We will have at the end demand curves for good examples, not really for one typical, because a really typical demand is not existing at the end. So we try to get really, I would say, a good example. That means it's also more or less a middle of the road example, probably a detached house or condominiums or something like this, but not too special because, for example, a tennis hall where you can play tennis make no sense because it's so special to get the demand for this. So we always want to get this demand curves for more or less typicals, but only typical examples, not more. Not more is not possible. And all this data had to be standardized in a, for example, CSV format at the end. And we have to have some additional data, for example, like prices and so on. This was the aim. Now the next slide, what is the current status at the moment? We have established all the internal servers to exchange the data sets, so these open energy data platforms. The data for renewable generation is or will be available on the large scale. This is thanks to DLR possible. It's on the demand side. We are looking for the low-hanging fruits for thermal and electrical yearly data sets from Denmark, Canada, and Germany. And here it's written, demand data, emphasis on being exemplary data. It's not really typical, it's an example. This could be, for example, in this case, a small district with 15 detached houses in Denmark. So we get the data set for the heat demand for the whole year on an hourly resolution for 15 detached houses in a small heating grid there in Denmark. The problem is that there is no claim to deliver typical or scalable data because generation is scalable. Or the data sets are scalable. If you have a photovoltaics with 10 kilowatt and you get your generation curve and you say, okay, I will install not 10 kilowatt, but 1 megawatt. You can multiply it by 100 and you will have the same generation curve. But if you have demand data, you can imagine if you have the demand for one detached house, you can't multiply it by 1,000 to get the result for 1,000 houses because there's always a balance in between all the houses of the peaks and so on. So generation is scalable. So that we can deliver typical data. On the demand side, it is not scalable, not in this case. So we have to say we give examples, but you could scale it up a little bit if you have a region with 100 houses. Then you can make a scale up more or less for 200 houses or 300 houses. But it's not possible from 1 or 2 or 3 to go to a bigger amount of houses. So I hope this was clear. We have learned this problem while working on this subtask 1. So subtask 2 is the main point of our activities. This is the approach to get all the mathematical descriptions of the storages as mentioned in level 1 and 2 in this case. And we tried also to define it as a white, gray, or black box model here. And I would say this model 3 level was more or less a white box model. So level 2 is a gray box model. It's something between, and level 1 is more or less only a black box model at the end. So what is the current status at the moment? Sorry, this is a starting point. I want to go there to the current status. We have two subgroups, one thermal, one electrical, as mentioned. And there we have a process established where we could bring together all the different models at the moment. For the reviews, it's finished. It's the RFB from, that means redox flow from South Korea. We have some lithium-ion chemistries from the CSEM from Switzerland. There are some acronyms like NMC, NSCA, LFP, LTO. Is all types of chemistry for lithium-ion batteries. And also for the sodium-ion battery from ETSAP. For other models, the process is still ongoing. We are working on this compressed air energy storage here at Fraunhofer Umsicht. And there is the idea to have a more general approach from the University of Calgary on lithium-ion, because I always said we have as a source this level 3 model. But there was a discussion, there is not a need to have this model. There's also a big data approach. That means if you have had many, many data sets from existing lithium-ion batteries that are running, when you get all the operating data, then you can also derive from this operating data a model for the storage device. And so this is the, I would say, the attempt to qualify this approach, if it is possible, to develop or to derive a level 2 model from this data set and not from a level 3 or white model. But this is under examination at the moment. The subtask 2, the thermal side, it is a little bit more complicated. As everybody knows who is in charge with thermal storage devices, while you have an electric storage device, this is more or less a single unit. You can buy a lithium-ion battery. But the thermal storage is in many cases, not in all, but in many cases, very close integrated to the whole system. So if you have a building with a pit hole storage or something like this, then the generation of the heat, the storage, and the building is more or less very close together. And there are some, there's the idea to have the optimum of all the three, but it's not viable as a single unit, this storage device, in most cases. I would say a stratified tank could be bought, but many, many other devices are very linked to the process itself. And so this is more complicated to make this modeling here. At the moment, we have collected all the different models existing, and we have discussed how we could match the subtask 2 with subtask 3, because subtask 3 is very combined with subtask 2 in this thermal field because of this strong interconnection between the application and the storage model itself. So this is the way to go to subtask 3, the application there. At the moment, we have this application done, for example, by the DLR with the remix model, but also with other partners from the group running, for example, some times modeling, including the ETSAP groups there. And we have established the first open source platform, but this is more internally. We want to go out at the end. There are two reasons to go out with this. On the one hand side, we want to meet the public, because if you have your own open source data service, it could be public, but you have no followers. And so we want to go to some existing, well-known, very established open source platforms. Some here are linked, like Open Power Systems Data.org or Wiki OpenMod Initiative.org, something like this. But this is we want to go at the end of our task, and not in this time at the moment. There we have an internal system run by the NSC. So let's go directly to the current status here. So we have divided in three subgroups there, as mentioned before. We have made some documents here to give summaries on the different subtask 3 application models at the moment. That means a comprehensive list of energy storage applications by scale and type. Type means thermal, electrical, or hybrid system. The next steps of this subtask 3 will be to cross-reference the models of the overview document with the subtask 2 models, as mentioned before. That means we are mixing up the models with the application. You can see here some screenshots in the tables. what is the application framework, the model source, for example, what is the status, and there something is complete, pending, on hold, and so on. So this is under this is on the workbench at the moment. So let's have a look to the collaboration and participants. There are 3 slides at the moment. We have a good cooperation with the ETSAP group from the IEA. This is good. There we also have a common workshop to get more understanding what is going on in this ETSAP group and to learn more about Times-Markal model. This Times-Markal model, for me, when I began with this annex, it was clear this is a Times-Markal model. And I've learned in this last 3 years, this is not the Times-Markal model. There are many, many different models existing in the frameworks of Times-Markal. And there are so many different applications for this modeling. So it was very interesting to have this exchange. And so we try to refocus our work a little bit in this case. So this is very important. And what is not mentioned here on the slide, we have had a discussion with the IEA headquarters with their own modeling system, but there are some differences in this modeling there. So it is not fitting as perfect as this ETSAP group at the moment. Let's have some outview on our participants. You can see there are many participants. Currently, we have 43 participants on our list, 20 organizations, 11 countries. And as normal, these are many, many people there. The core active group are less in most cases. And we have had the last meeting as the first real live in-presence meeting. That was really a pity to have all the online meetings before. And so I want to share some of the pictures we have had in Canada this fall. This was a meeting there with all the participants from Europe and from Canada. And you can see on the pictures there were some discussion rounds there and so some leisure time around there. And some sightseeing, sightseeing with the IEA means it's a technical tour and not really sightseeing. This is more technical sightseeing. But you can see on the right-hand side, there are also wild turkeys. This was our wild turkey moments there. They are existing. That was in Canada really funny because all participants were very excited because of this wild turkey. Nobody has never seen before wild turkeys. And afterwards, we were in this building. It was this building. It was a battery testing facility. And these guys were totally annoyed of all the wild turkeys around. So it's different approach to this natural behavior there. On the other hand side, there was this building. It's the building from the University, Carleton University. And this includes a real building with a real storage, seasonal storage underground. And they try to make many experiments with this to learn more about the options of seasonal storages for detached houses here. So these were our last slides, and this is very important to everybody who is working in the framework of the IEA. The framework of the IEA is more or less, it's a group of people who have a common interest. So it's not as strong as a project with really concrete timelines and all the pushing factors like money. It's not existing. So it's more like it's relying on the interest of everybody who is joining. This is the main point. And so it was very important to have some in-presence meeting, because to get with the new groups, the social glue for collaborating is not so easy. And it was a very late first meeting. That was really a pity, but it was a first meeting. And so we were very happy about this. And with this comment, I want to close more or less my presentation with a typical graphic to this, and I'm open to all your questions, your interests, and so on. Thanks a lot.
Okay, many thanks for your talk. It's really how to say, impressive how many different types of energy storage are considered. I can imagine that this is a lot of work to gather all the information and to validate the data and everything, I imagine.
Yes, and to limit also the scope, this is also a problem because more or less energy storages are not really unlimited, but it's a big bunch of possibilities also on the thermal side. So you have to limit it because we are not a so big group. It looks big with 42 people, but at the end, the active group is more or less 1 to 3 handful, I would say.
Yes.
I have only 2 hands, but 3 handful. That's realistic. And this is important point there. We have to have a realistic aim at the end, which we can fulfill or which we can meet at the end summer next year.
Yes, this can imagine. You need more hands and more participants. So I'm not sure if anyone already has a question, so please, you can raise your hand with the reaction button, or you can write into the chat. Okay. The one hand raise, I can see how.
Emily, Noel?
Yes, it's me.
Thank you.
Thank you for your presentation. I am from EFPM, so in French, and I'm sorry I didn't get the beginning of your presentation, but what I understood is you try to have a simulation of energy storage in going from generation to demand and to know if the energy storage can give some things. And to do that, you need to build some bricks to know how modelize energy storage. And you have done some things about batteries, but also from the compressed air. And this is here I want to go. In my company, we are working on adiabatic compressed air energy storage. So we have a simulation model for that. And I am wondering if perhaps we can give you some input on that. In order to help you to construct the bricks for this case, and it will be good for us to know if with this brick you can we can have a business model or something interesting.
Yes, this is very easy for me because the adiabatic compressed air energy storage is modeled by Fraunhofer Umsicht, and so because we do this by our own, it would be always good to have some exchange with some other partners regarding this modeling. On the one hand side, we have really good experts. We have here 2 different PhDs done on the adiabatic storage systems. But to discuss this with some expert who have done the same probably or something comparable would be very, very valuable. So if you could drop me some lines in an email, I will make the contact to our experts from our group modeling this compressed air and from our group who is acting in this annex. These are 2 groups because we have the expert group and the guys who are engaged in this annex, in this task, sorry. And would be great. Write me some lines and I will make the contact, and it would be very, very nice to get the exchange and to get more information about the compressed air storage from your side.
Okay. Thank you.
Okay, so do we have another question? So in this case, I might take the chance and ask, due to the fact that I'm working on thermal energy storages as well, I mean, I know it's quite mean because, as you said, the thermal energy storage is quite a tricky tool to work with if it comes to some summarized simulation. But how did you distinguish between industry and industrial use, where you have the higher temperature and very different kind of storage material you might use in storages and temperature regions, and the households where you are, let's say, mainly below the -degree scale?
You're totally right. If you have some industrial applications, then you have other temperature ranges. This is at the moment not included because this was a limitation to say, if you go to the industrial applications, it's unmanageable. There are so many different industrial applications on every temperature level existing between, I would say, 80 degrees and 1000 degrees if you go to a steel mill, for example. So this is not included. So we can't give you a model for the steel mill or, for example, for a big chemical plant with 350 degree storage. This is not included. It's more or less focused on, I would say, energy by housing and something like this, and smaller units, probably like some retail shops and something like this, but not really like industry, because it's so complex and so big differences in this. This is not included, but we have some models for this, but not regarding these tasks. This is more from my colleagues from another part of Fraunhofer. They are dealing with this, but not in this task.
Okay, thank you. Yeah, I guess once this task is finished, it's quite nice to top it up with all the different things that's coming.
It's also too late, to be honest, but it was also at the starting point too complex. We have so many examples. We decided to say, no, that's not possible. No, it's too complex. There are so many very special applications for thermal storage in industrial applications. It was impressive, but also awful, both in the same case.
And they're quite customized, so it's
yeah, it's really customized, totally customized the storage then.
Okay, yeah, thank you. So we have a question from Joris Korniv. Sorry if I pronounced it wrong. Please go ahead.
No, thanks a lot. Very interesting presentation, Christian. Thanks for that. I'm Joris Korniv. I work at TNO, basically the Dutch Fraunhofer Research Institute here in the Netherlands. My question is about, do you, for the energy storage options, can you also model like other markets than just the imbalance market? So just where you have a surplus of energy or you have a shortage of energy, typically you can buy that on the market and sell it at a higher price or buy it at low price, the arbitrage business case. But can you also model basically the, for instance, frequency control market for batteries or like the other services?
That's very easy to give an answer, because this is not the core part of our annex. Our annex is really to develop the models for the storage devices. Okay. We do this, what you have asked. For example, in the applications, it could be used, but for regulation, I don't think that we have some people working on this. Arbitrage, as far as I know, the DLR is running the optimization system for this, so this is existing, but this is not, I would say, it's not developed and not open source in this part. It's more a part coming from the outside, from the partners, because they have done it before. They have this, for example, this application, as you mentioned, for different storages, and they develop with us the modeling of the storage device, but not the application at the end. That's the point.
Okay, no, that's clear. Thanks. Yeah.
Okay, many thanks for the question. Do we have another one?
Probably you could come back to yours to explain why it's not included. It was also on the starting point 4 years ago, the starting point to discuss this. And if you have a look to all the economic figures, if you want to go some different markets, we decided the European market is so different in many cases. It's so difficult, all the regulations you have to fulfill sometimes, that we're not able to do this on the level of Europe. And we have to keep in mind the states from Asia or from North America, and said, no, we are not able to do this. You can only use our models to do this in the country, is all the expertise on the special market of this country, but we can't deliver this. This was really too broad. It's interesting, this question, but it's too broad to this IEA annex.
No, I can imagine. Yeah. Now maybe, and also, if we have the discussion anyway, we're also working a lot on the subsurface energy storage of heat in our department.
What storage? Sorry.
The subsurface storage of heat. So you mentioned pit storage in your thermal systems, and we work a lot on the aquifer storage option, which is also relevant in some parts of the European continent, basically. And for that, we also have delivered, basically a bit the same kind and type of modeling, like proxy modeling for the storage device, but also feeding it into system models to see how you can use a model for in a district heating grid, for instance.
If you call this all this pit storage, aquifer storage, and so on, I would give you the hint always to contact our partners from Denmark, for example, Alireza, because you know, the Germans relied on Russian gas for heating, and we have not so many heat pumps and so many thermal storage devices. We can discuss about this in another discussion probably, but this is the reality. And so all the aquifers and so on is not so common in Germany, to be honest. It's more in the northern states, like Denmark, for example. I know you are in the Netherlands, you are not relying on the natural gas since 10 years, I think. That was very clever from your side. Congratulations. But in Germany, we have, I would say, taken the wrong path. And so many technologies are not established on the heating side at the moment here. And so also not the storage devices.
Yeah, no, true. No, I think, we are still also relying on natural gas, I'm afraid, a lot in the Netherlands. But
but you have your own producer sometimes, and as I know from your side now, it's declining the natural gas and also not connecting the detached houses to the natural gas grid. And in Germany, we did this up to January this year. Always it was recommended take the natural gas for heating. That's it. Period. Yep.
Thanks a lot, Christian.
But there's not an annex for this problem at the moment, to be honest. And the IEA is not fast enough for something like this. Also not Fraunhofer, to be honest. More questions?
Okay. It doesn't seem so in the moment. In the chat, there is just a comment from Andy Cruden. He thanks you for the talk. He had to leave already, but just so that it's not overseen.
Yes, Andy was at the last meeting. I know Andy.
Okay.
Goodbye.
Perfect. Okay. If there's no question, I would say we can close the session. Thank you again. It was really very nice insight into the task 32. And I'm very curious about the final report then. And on the open source, the solution, I'm really curious to see it. And many thanks again for the listeners and for the discussion and for you, the speaker. And I wish you a nice holidays as they're quite around the corner. And a nice evening or afternoon or day. I'm not sure from where you all listen, but have a good time. Bye.